Welcome to week 3 of lecture 3 of week number 2. So, in the last class we discussed about finding out the equivalent elastic modulus of composite along direction 1. Now, before going to the other elastic moduli and Poisson's ratio, we would spend some few more minutes on discussing what we derived in the last class and some continuation of that. So, in the last class we derived that elastic modulus in direction 1 E f is equal to V f multiplied by E 1 f plus V m multiplied by E m. Now, if we want to find out the load carried by fiber F 1 P 1 f as compared to the total load. So, we had a diagram like this and we saw that there is a force P acting on and the force P is distributed between fiber and matrix. So, if you want to find out what is the proportion of the load P that is being taken by fiber, we can find it out in this way. The load in the fiber is stress in the fiber, which is sigma 1 f multiplied by the area of fiber divided by the total force P, which is sigma 1 m multiplied by A m plus sigma 1 f multiplied by A f. And we have seen that sigma 1 f is E 1 f multiplied by epsilon 1 and then we have A f here and this is E m multiplied by epsilon 1 and we have A m multiplied and we have E 1 f multiplied by epsilon 1 with A f multiplied. Epsilon 1 gets cancelled because they are present in both numerator and denominator, and if I divide the numerator and denominator again by A m plus A f, we get the volume fractions in numerator and denominator, and that gives us E 1 f multiplied by V f divided by E 1 f multiplied by V f plus E m multiplied by V m. So, the ratio between P 1 f and P is just this. Now, again we can write this V m in terms of V f and entirely write this expression in terms of fiber volume fraction, we can do that. Now, if we see in general E 1 f is more than 10 times of E n in most of the cases, in most of the fiber and matrix combinations. With that, if the fiber volume fraction is about say 0.25, then P 1 f by P is generally over 75%, and again in most of the cases our V f is much more than 0.25, this goes up to 0.6, 0.65 like that. So, we can see that in the longitudinal direction most of the load is taken by fiber, and also the relation that we derived. So, if you want to plot the variation of E 1 with fiber volume fraction, the plot is linear and it looks like this. So, this is 0 and this is 1. So, when there is no fiber, that means fiber volume fraction is 0, only matrix contributes, that is one extreme. The other extreme condition is that when there is no matrix, the entire thing is fiber. In that case only fiber contributes. and in between them there is a linear variation. Okay, so now we will move on to the transverse modulus. That means elastic modulus in the direction perpendicular to the fiber direction. So, again if we go back to that idealized fiber matrix combination diagram, which looks like this. We have fiber in one side and matrix in one side. Again this line does not mean it does not necessarily mean the fiber direction, it just means that it is separate and this is separate. The fiber direction is along the axis 1 and the transverse is axis 2. अच्छा इस स्लाइड टाइम आरेकबार বলি বুঝলেন এটা আঁকা ঠিক হয়নি। So, now we are going to move on to the transverse modulus. That means the elastic modulus along the direction perpendicular to the fiber direction. So, for that we will again go back to the idealized fiber matrix combination diagram. So, we have fiber in one side, matrix in other side, and previously we were loading it along this direction, but right now instead of that we will load it in the other direction because our quantity of interest is different. So, we load it in direction 2 and let us say this is our direction 1, this is direction 2. So, now this is loaded in the transverse direction in the direction 2. So, when it is loaded in this fashion, the deformed shape is going to look something like this. So, it is going to be extended in direction 2 and due to the Poisson's effect it is going to be contracted in direction 1. In the previous case the extension was in direction 1 and the contraction was in direction 2, here it is opposite. And in the previous case our assumption was the fiber and matrix they have same strain, but the stress is different. In this case because the load is along direction 2, we cannot have different stress at fiber and matrix, otherwise the equilibrium at the junction between fiber and matrix will not hold. So, here the consideration is that the stress in fiber is same as stress in matrix. So, sigma 2 stress in direction 2, normal stress in direction 2 in fiber is going to be is equal to sigma 2 m, and let us call it a quantity called sigma 2. Now, because sigma 2 f and sigma 2 m are different and the elastic modulus of the constituents are different, so the strains are going to be different. So, we can say that the total amount of elongation in direction 2 is the sum of the elongation along direction 2 for fiber and the direction 2 for matrix. So, let us say that this dimension for fiber is T f and this dimension for fiber is T m. So, total elongation of the fiber domain along direction 2 is epsilon 2 of fiber multiplied by T f, because epsilon 2 is the normal strain in direction 2. If I multiply this strain by this dimension T f, that is going to give us the total elongation along direction 2, we can call it sigma 2 f delta 2 f. Similarly, delta 2 m, that means elongation in direction 2 for the matrix is epsilon 2 m multiplied by T m. So, the total elongation in direction 2, which is called delta 2, we can write that as delta 2 f plus delta 2 m, and this we can write as delta 2 f T f, sorry, epsilon 2 f T f plus epsilon 2 m T m. Now, like we defined an equivalent stress in the previous case, we would define something called equivalent strain in this case. That means, an averaged out strain epsilon 2 averaged out over the fiber and matrix. So, if that is supposed to work over the fiber matrix combined region, then the total elongation due to that can be written as epsilon 2 multiplied by Tf plus Tm. Now, this epsilon 2 f, that means normal strain along direction 2 for matrix, can be written as epsilon 2 f divided by E 2 f, where epsilon 2 f and epsilon 2 m are same. So, that is sigma 2 f divided by E 2 f, and where sigma 2 f and sigma 2 m are same, and that is equal to a quantity sigma 2, and E 2 f is elastic modulus of the fiber along direction 2. Again, as we discussed, the fibers can have different elastic modulus along direction 1 and 2. So, we denote it with a suffix 2. Similarly, epsilon 2 m we can define, and that as epsilon 2 m divided by E m, and that is sigma 2 m by E m, and that is sigma 2 by E m. Similarly, this equivalent strain epsilon 2 can be written as sigma 2, that same stress, divided by our equivalent elastic modulus of the composite along direction 2, which is E 2, and that is our desired quantity. So, if I substitute all these things here, we can write this as sigma 2 divided by E 2 f multiplied by T f plus sigma 2 divided by E 2 m multiplied by T m is equal to sigma 2 divided by E 2 multiplied by T f plus T m. Now, we can take this T f plus T m here in the denominator, and we will get a quantity like this T f divided by T f plus T m, and again a close observation says that this is nothing but fiber volume fraction V f, because the the dimensions of this are V along x direction, and also the direction 1, and also the perpendicular direction 3 is same. So, T f by T f plus T m is V, it is same, I mean these directions are same for both matrix and fiber. So, whatever, if I want to find out the corresponding volume, then whatever I multiply here, and if I multiply by the corresponding volume here, and whatever multiply here, they are same. So, this gives me V f. Similarly, I have T m divided by T f plus T m, and that will give me V n, and sigma 2 is common in all the terms. So, with that we get V f by E 2 f plus V m by, and also because matrix is homogeneous, we really do not need a suffix 2 here. So, V m by E m is equal to 1 by E 2. So, this is another important relation that we get, and this says that the reciprocal of the elastic modulus along 2 of the composite is equal to a weighted combination of the individual reciprocals of the elastic modulus of matrix and fiber. Here the weight factor is the again the volume fractions. Now, there are some numerical relations of E 2 with E m and E f that was given by Halpin and Shai. Again, the interested learners can read this paper. So, and those are famously known as Halpin and Shai equations, and that numerical relation, that empirical relation says that E 2 m is equal to E m multiplied by 1 plus xi 1 eta 1 multiplied by V f divided by 1 minus eta 1 multiplied by V f. Here eta 1 is again related to the individual elastic modulus and xi, and the relation is this, and xi 1 is something that we can control, that is known as reinforcing efficiency factor, and this depends on few parameters. They are fiber geometry, and packing arrangement or packing geometry, and also the loading direction. So, this is an empirical relation where xi is a parameter which we can control, xi 1 is a parameter that we can control, and depending on the fiber geometry, packing geometry and loading direction, this xi 1 can be different, and that gives us different value of E 2. So, whatever we derived just now based on the strength of material based approach, that does not have any provision which makes E 2 dependent on these parameters, but here E 2 can be dependent on these parameters, fiber geometry, packing geometry and loading direction. So, for example, the fibers which has circular in cross section, for example, circular fiber in square array. So, if the fibers are circular and their arrangement is a square arrangement, then xi 1 is equal to 2, and if they are a rectangular fiber, and the fiber has a dimension a by b, if it is arranged in hexagonal fashion, then xi 1 is equal to 2 multiplied by a by b, where b is in the direction of loading. So, say this is the composite, and if I look at the cross section, the fiber arrangement is, the fibers has a cross section like this, and if the cross section of the fiber is here, the dimension is b and this dimension is a, and the load is in this direction, it is transverse load. That means, b is along the direction of the load. So, with that we can say that xi 1 is 2 into a by b, provided it is arranged in a hexagonal fashion. Now, we will move on to find, before that let us just plot the variation of E 2 with V f, like what we did for the longitudinal case. So, here their reciprocals are maintain a linear relationship. So, the actual terms maintains a relationship like this. So, again in the extreme case, when V f is equal to 0, E 2 is equal to E m when Vf is equal to 1, E2 is equal to E2f, and in between that it follows a curve like this. Now, we will discuss about the transverse the shear modulus. Shear modulus in the 1-2 plane. Again, let us go to our idealized diagram with fiber being in one side and matrix being in the other side, and let us say that now we are loading it in shear in the 1-2 plane. So, this is direction 1, this is direction 2. So, let us say that there is a shear load tau, this is tau 2 1, tau 2 1, tau 1 2, tau 1 2. Now, we know that the effect of shear is something that cause distortion. So, if this is under shear, a shear like this, it distorts to something like this, that means a rectangle becomes a parallelogram. So, this angle 90 degree is not preserved, so it becomes a different angle. So, the change in angle, so whatever this angle is, if I subtract this angle from this 90 degree, then whatever we get, that is the measurement of shear strain. Now, if something has less shear modulus, the distortion is more, with higher shear modulus the distortion is less. Now, fiber and matrix have different shear modulus, so that means that their distortion is going to be different. So, if I draw the distorted diagram of it, it would look like this. So, first the matrix part, which shows a higher distortion because of less shear modulus, and then the fiber part, which shows lower distortion because of higher shear modulus. So, the end effect is the point which was here has moved here. So, the point which was initially somewhere here has moved to here. Similarly, here the if I look at this point, so initially it would have been somewhere here and this has moved here. So, that is the total delta due to shear, and again it can be broken into two components, a delta due to shear in the matrix and a delta due to shear in the fiber. So, we can call it delta m and delta f, and also this angle is the shear strain in matrix and this angle is shear strain in fiber. And again let us say that the dimensions are Tf and Tm, and again for equilibrium at this junction the shear should be equal. So, tau 2 1 in the fiber should be is equal to tau 2 1 in the matrix. Now, let us write delta m. So, delta m is, if gamma m, the shear angle is small, then we can say that delta m is this gamma multiplied by this vertical dimension, and that vertical dimension is nothing but T m. So, delta m is gamma m multiplied by T m. Similarly, delta f is gamma f multiplied by T f. Now, the total delta is delta f plus delta m, and this can be written as again delta f we have seen, this is gamma m Tm plus gamma f Tf, and that is equal to total delta. Now, what we do is we would assume that there is a equivalent shear strain working, and that shear strain we can call as just gamma or gamma c or gamma. So, that gamma multiplied by this total dimension Tm plus Tf is going to give me the total delta. So, gamma multiplied by Tm plus Tf is going to give me that same delta, which is a combination of delta f plus delta m. Now, gamma m can be written as del 2 1 m divided by G m, that means shear stress divided by shear modulus of the matrix, and del 2 1 m is equal to del 2 1 f, let us call it tau 2 1 f is equal to tau 2 1 m, let us call it tau 2 1. So, it becomes tau 2 1 by G m. Similarly, gamma f becomes tau 2 1 by G 1 to f. Now, again these fibers can have different shear modulus in different plane. So, just to have that provision we are writing it as G 1 2 with G 1 2 being equal to G 2 1. So, G 1 2 fiber is equal to G 2 1 fiber, and likewise we can define an equivalent shear modulus of the composite, and that we can define as simply G 1 2 and that is equal to G 2 1. So, then we can write gamma is equal to tau 2 1 by G 1 2. Now, we can put everything here, and that gives us tau 2 1 divided by G m multiplied by T m plus tau 2 1 multiplied by G 1 to f multiplied by T f, and that is equal to tau 2 1 divided by G 1 2 multiplied by T m plus T f. Now, again we can take this T m plus T f in the denominator here, and then we again get the same ratios T m plus T f, T m divided by T m plus T f, and that gives us V m, and again we have that quantity T f divided by T m plus T f, and that gives us V f, and tau 2 1 is same in all the terms. So, we get V m by G m plus V f by G 1 to f is equal to 1 by G 1 2. So, this relation is again same as what we got for the transverse case. So, the reciprocal of G 1 2 is equal to a weighted combination of G m and G 1 to f, where the weight factor is V m and V f. Now, if we again want to draw the same diagram showing the variation of our desired quantity G 1 2 with fiber volume fraction, we again get a similarly looking diagram. The relations are same. So, we have G m here and we have G 1 to f here, and this is 0 and this is 1. Now, for shear modulus also there is equation given by Hall Prince I, and that equation is quite similar to what we saw for the previous case. So, G12 is equal to Gm plus multiplied by 1 plus xi 2 eta 2 Vf divided by 1 minus eta 2 Vf, where xi 2 is called reinforcing or reinforcement efficiency, and again it depends on the same set of parameters like we saw before, depends on fiber geometry, packing geometry, and loading direction. And also eta 2, its dependence on xi 2 is also similar to what we saw before. So, this is xi f plus G12f plus xi 2 multiplied by Gm. Now, xi 2, the values are a little different. For example, here xi 2 circular fiber square array gives us xi 2 is equal to 1, whereas rectangular fiber hexagonal array gives us xi 2 is equal to root 3 log a by b with the base of the log being e, where b is in the direction of load. Again, to understand that, let us draw a similar diagram what we did before, and let us say that we have a rectangular cross section fiber here with this being B and this being A. Now, the shear load is such that at this face it is in this direction. So, the shear load direction is aligned with the B direction. So, that is why we are saying that B is in the loading direction, and accordingly that we get xi 2 as root 3 log of A by B. So, again this has a provision that depending on the cross section, array packaging and loading direction, we can vary G12. So, with that we will end the discussion here. In the next class we will look at the Poisson ratios. Thank you.